Very wonderful. Good evening, good afternoon, or good morning, wherever you are, and welcome to Calling Functions, a tutorial. Allow me to quickly introduce myself. My name is Klaus, and I'm working as a freelancing C++ trainer since approximately 2016. Apparently, doing C++ on my job is not enough C++ for me. I'm also doing C++ on my free time. For instance, I'm the author of a C++ math library called Blaze, and I'm also one of the organizers of the Munich C++ user group, which, as a side note, may actually be one of the largest and most active C++ user groups worldwide. This talk is about calling functions. And in particular, this is about the individual steps, the mechanical steps that happen when you call a function. It is not the low-level thing that happens in a compiler or in a CPU. It is truly the individual steps that the language itself defines. So we will take a close look at name lookup. There is a step called template argument deduction. We'll take a close look at overload resolution, access labels, function template specializations, virtual dispatch, and deleting functions. So this will be quite a challenge for a 60-minute talk. This is also why I can unfortunately not go into detail about every single detail. I will, for instance, not be able to talk about template argument deduction. There's excellent material on that, however, so this should get you covered. And I also will not be able to talk about virtual dispatch. Else, we will indeed get a complete overview of all the individual steps, how they're connected, and why sometimes calling functions is a pretty surprising endeavor. Still, I should give you some ideas what you can expect and what you cannot expect in this talk. So this talk does focus on the basic mechanics indeed, primarily because I found that this is teaching material that is missing, has been missing so far. You find the details, but not really in one talk putting them together. I will also point out the surprising details. And whenever necessary, I will give you further references to other talks, other material, whenever it is appropriate. This talk does not show all possible examples. That is hardly possible. Then we would probably need an entire day to even get close to that. And it also does not mention every single detail. So I will, for instance, not give you every possible case in overload resolution. I believe as soon as you understand how it works in general, you will have an easy time to deal with this yourself. And it also does not try to be bleeding edge. So I will stick to the important details and I try to be a C++ 20 talk. So with having said that, let's first of all get an overview of the individual steps in calling a function. The very first step is called name lookup. The purpose of name lookup is to first of all find possible candidate functions so all functions with a certain name. We'll see exactly how this works, but name lookup comes up potentially with quite a number of names. The second step, directly taken afterwards, is template argument deduction. Some of these candidate functions might actually be function templates. These function templates need to be instantiated in order to produce functions that we can ultimately call. There's a couple of pretty interesting mechanisms at work here as well, such as SFINAE. As I said, unfortunately, I cannot go into detail here. But imagine that now I extended the set by some additional functions, and this additional set of candidate functions now goes into the overload resolution. The purpose of the overload resolution is to find the one function that we deem to be the best match. It might not be a perfect match, but from all the given candidate functions, we find out which one fits best. This one function might actually be a member function. Then we should take a look at the access labels, so see if it actually can be called. The one selected function might be a function template. Then we also have to consider function template specializations, which is not quite as obvious as it sounds. And the selected function might be a virtual function. In that case, we have to trigger a virtual dispatch. And the last possible case is that the given function might actually have been deleted explicitly via equal delete. So all of these steps now are explicitly dealt with. We now walk through these individual steps and talk about all of them individually. Before we get started, there is one comment that is actually fundamental to understanding how a lot of these steps interact. This, let's call this algorithm, is a strict one-way street. Once name lookup is finished finding some function, and then I come to a compilation error later, I never go back to a preceding step. I always really report the error as error. Now, this is something that we'll see in a couple of places, and this is very important to keep in mind in order to understand the complete behavior. All right, with having said that, let's first take a look at name lookup. The very first step, dealing with just finding the functions that we are supposed to call. So the example I have is a function that takes a double, a function called f, then a namespace called namespace1, n1, with an additional function that takes an int. This is my function 1, this is my function 2. In the main function, I now call function f with a 1.0. Unsurprisingly, this will call function 1. This is called unqualified lookup. I do not explicitly make any specifications. I just find the function that is most appropriate. If I call f with a 42, however, I do not go to function 2, because at this point, the compiler does not even consider namespace n1. It only finds and exclusively finds function 1. This is the only match, and as we see later, it actually can be called. So again, unqualified lookup calls function 1. If from that call site, from the main function, I really want to call the function f in the namespace n1, I have to explicitly say so. I have to explicitly qualify with n1 : f. This now calls function 2, and this is called qualified lookup. Qualified lookup looks for a specific function. A function is specific namespace, or sometimes also class scope. Unqualified lookup finds the best match from the given call site. Now let's imagine that the function in the namespace n1 doesn't exist. I only have function 1. Then the first two cases will still call function 1. The last call, the qualified lookup, however, is now ill-formed. There simply isn't a function f in namespace n1. The name lookup comes up empty-handed and reports this is an error. It does not continue looking because it is qualified lookup after all. You are specifying that you want to call a specific function from a specific namespace in the first place. Now let's assume that I get my function 2 back, but that I have two additional functions, g and h. G calls n1 : f, h calls f without qualification. Both use a double argument. Now, the first function I call is the function g from the n1 namespace. N uses qualified lookup, and for that reason will definitely call function 2. Despite the fact that the double now, of course, has been squeezed into an int. This is called a conversion. So this calls, with a qualified lookup, function 2. If I call function h, then I would hope for perhaps that function 1 is selected. But perhaps surprisingly, this also calls function 2, this time with unqualified lookup. The name lookup tries to find the according function from that call site. The first thing that the compiler finds is this f. That is the only f in this particular namespace, the only f that has been seen so far. And so the name lookup is satisfied, finishes its job, and passes this over as the only viable candidate to the next step. This function is not even found by name lookup. This is what we call hiding. Function 2, because it has the same name, hides function f1. Hiding is a pretty important mechanism to keep in mind. The rationale is this must be the most specific function because it is closest to the call site. This is why the compiler does not even consider anything else. This is supposed to protect you from surprising behavior. And of course, in many situations, this works just as intended. We'll see a couple of places where this is indeed very surprising. This is even true if f takes a string argument. The compiler would only find this particular f, and so both calls, both the call from g and the call from h would be ill-formed. The compiler comes up with f, function 2. This is the only function that the compiler comes up with. And later, of course, in the overload resolution step, we find that this is not a match at all. It reports a compilation error. And as I said before, we never go back to try to find another f. At this point, overload resolution fails because the name lookup simply didn't find this function. So again, it's this hiding effect. Function 2 hides function 1. This is also true if we have types or any kind of variables. It is about the name. It is called name lookup. And so if we have a variable, constant, or anything with the according name, the name lookup would at this point find this. It would report it. Then later we would find that this f cannot be used as a function. So it is name lookup. It is not function lookup. Any name is taken into consideration. Now let's assume that the second function is gone again. Then function g is suddenly ill-formed. There is no function in the name in one namespace. Function h, however, now calls function 1. Compiler does not find anything in namespace n1 where the call originates, and for that reason only, it continues looking in the next scope, which here is the global scope. No f in n1. But then finally, I find an f in the global namespace. That must be the function call, and ultimately it is indeed called. So I now get my function 2 back, but I get rid of the explicit n1 qualifier. This is now explicitly specifying I want to call a function from the global namespace. For that reason now, f calls function 1 in the global namespace, and h calls, just as before, function 2. Qualified lookup versus unqualified lookup again. Note that nothing changes with regard to which function is called if I come up with a third function, a function f that takes a double in namespace n1. This function is only defined after the call site. So officially it hasn't been seen yet, so it cannot be considered. Name lookup only considers all those functions that already have been seen. And then, of course, as I said before, in order based on the namespace, based on the location of the call site. So function 3 is never an option for these two function calls. Let's introduce struct s, which also has a function f. Function takes an int, this is my function 3, and additionally comes with a function called g, which calls f with a double value. If in my main function I first create an s and then call s.g, then the first function that is found in this context is function 3. I first start looking in the scope of s, it finds the function 3, calls function 3. Both 2 and 1 are never considered because, again, of hiding. If function 3 is gone, then the compiler doesn't find anything in struct s, is free to explore the surrounding namespace, and finds function 2. Again, function 4 is not an option because it's defined after the call site. So function 2 is called, which, however, again hides function 1. And if I would get rid of the second function, then finally I would not find something in S, I would not find any f in N1, and so I would call function 1 without any kind of hiding. Note that so far we have only dealt with fundamental types. Still, the effects that I described are pretty important to keep in mind. And this is one of the examples that is always confusing to especially new programmers, and particularly programmers that come from Java or C#, languages that put more emphasis on class scope. I create now a derived object, and a derived object is deriving from a base class. The base class comes with two f's, an f that takes an int and an f that takes a double. This is function 1, this is function 2. The derived class introduces a third function, which of course overrides function 2. So this is my function 3. I use this d and I call a function f with a 42, an integer, obviously. Still, despite the fact that this is an integer, despite the fact that in this class hierarchy, eventually the name lookup might find a function that takes an int, this will call function 3. for exactly the reasons explained before. The one additional information is that the call here originates essentially from the scope. I looking up a function from the scope of derived. Name lookup finds a function f, function 3. Because it finds a function with the according name, it does not continue looking elsewhere. So this function ultimately is called because I can convert an integer into a double. Function 1 and 2 are again hidden. The compiler cannot see them, and therefore they're not taken into account. This is confusing. This is something that surprises people. This is something that really should remember. Now, as I said before, so far we have only and exclusively dealt with fundamental types. Let's introduce a class type, struct s, which is empty, but which comes with an additional function f that takes an s. Now a special effect comes into play. I create an s, and I pass this s to a function f. Despite the fact that I said before that only the things that have been seen are now called, actually this will call function 3, a function that is not in the global namespace, but in namespace n1. This effect is called argument-dependent lookup. The type s is from the namespace n1, and so the compiler is now additionally considering the namespace n1 to find functions. So in this context, it finds both function 1, 2, and 3, and then ultimately decides that function 3 is the right thing to call. All functions are taken into account because of the namespace of one of the operands, one of the arguments, hence argument-dependent lookup. If I would introduce a function g in a global namespace prior to namespace n1, and the thing that I pass, this t, would call the function f, could be any type here, function template. And if in my main function I call g and pass an s, still function 3 would be called. Despite the fact that g is defined before the namespace n1, and so itself hasn't seen this f, due to the late instantiation of this function, still this is taken into account. Argument-dependent lookup works perfectly in this context. Note that I said it additionally takes namespace n1 into account. If I would introduce another f in the global namespace that takes an n1s, then a call to any f via g or f directly would actually be an ambiguous function call between function 3 and 4. The compiler would now find all these functions, and 3 and 4, unfortunately, are so similar that the compiler cannot decide which one is better. This is the point where we say a function call is ambiguous. Yeah, we'll revisit this again when we talk about overload resolution. But it finds both 3 and 4, both are equally well matched. The compiler will fail in the overload resolution stage. So, guideline, remember that argument-dependent lookup only works for user-defined types. It does not work for fundamental types like int, double, pointers, etc. There is one additional thing that I want you to remember. Let's imagine that my s has a swap function that is supposed to swap to s. Now, at some point, for instance, in a generic function g that takes 2 arguments, I am calling the swap function. So I have 2 s's, s1 and s2. I call g, actually with s1 and s2, type on the slide. These 2 s's are supposed to be swapped by means of this function, which is actually not what is happening. This will call std swap. So it will call the function that I explicitly asked for, std swap. In order for ADL to work, I have to really use unqualified lookup. So the advice here is not to qualify swap, but to say using std swap and to call the function unqualified. Standard swap is now an option, but since I do find a better match, thanks to argument-dependent lookup, the right swap function. So the swap that swaps to s is called. So prefer unqualified name lookup to qualified name lookup. And especially in generic code, consider core guideline C165 using for customization points. This and only this will allow ADL to do its job properly. Now, there's one more effect in name lookup that I should mention, and that is called two-phase lookup. Let's consider a function f that takes a double. This is my function 1. Again, function g from before. Now an additional function 2 in the global namespace defined after g. And again, the struct s with the according function f. This is my function 3. If in a main function I pass an s to g, then this will actually call function 3, the right function, based on argument-dependent lookup. Because this works so well, many people would expect that the next call, g of 42, will call function 2. But it doesn't. Or let me say it shouldn't. Some compilers actually did this wrong, so some years ago. Now hopefully everything's fixed. This should call function 1. This is a fundamental type, and so all the rules for fundamental types apply. Function 2 has not been seen officially at the point where g is defined, so only function 1 is an option. And so this function should ultimately be called. Since g is instantiated only at the point of call, and since therefore there is kind of two phases for looking up things in templates, it's called two-phase lookup. Still, the rules that, as I've explained them before, are in effect. Argument-dependent lookup for class types and the regular lookup for fundamental types. So this concludes lookup. If you have any questions, please note them down. I will answer any kind of question at the end of the talk. Please also additionally note down slide numbers, which will make it much, much easier to go back to a specific slide. So the next thing that we are taking a look at is template argument deduction. Template argument deduction, however, is a pretty complex beast in itself, and so I defer you to a talk from CppCon 2014. Scott Myers had talked about type deduction and why you care, and this is over 1 hour talk just about C++ type deduction. I'm not aware of any talk that summarizes this better. This really explains how type deduction works, the simple cases, but also the more complex cases. There's also another effect that you might consider, something called SFINAE. Also here, I have hardly enough time to mention it, but there is a good talk about this special effect given by Arthur Dwyer called a soupçon of SFINAE. So as he himself says at the very beginning of the talk, the hardest thing about this talk is probably the title. Soupçon means a very small quantity of something. So it is intended to be a beginner-friendly introduction of something that's not necessarily beginner-friendly. So watch this talk, or any other talk about SFINAE. They will give you a pretty good idea what to expect here. Which, however, brings us directly to the third step, overload resolution. Overload resolution is probably one of the most complex steps in this entire thing, and definitely also takes a lot of space in the standard itself. Overload resolution itself is split into 2 steps. The first step is to compile a list of viable candidates. So from all the functions that I get from both name lookup and template argument deduction, figure out which functions are actually callable by the given arguments. So what is a viable or not viable candidate? So assuming that I have a function f where I pass a 42, a single argument, a single integer argument, then a viable candidate could be a function that takes an int. That would be a so-called identity or exact match. It could be a function that requires me to pass a constant in ref. This is called a trivial conversion. I simply add a const to this int, which is always possible. This is fine. I could also call a function that requires me to convert the integer to something that it can be converted to. So a standard conversion. I could also call a function that uses or expects a class type, because this class type might actually have a non-explicit constructor that allows a conversion from a particular argument into a class type. Then this function is an option. I could also call functions that take more arguments, but where all the arguments that I do not pass explicitly have default arguments. Also, all the functions that have matching constraints are an option. So this function expects any kind of integral, and so this works splendidly. And of course, as a last resort, all functions that take ellipsis arguments also would work. Non-viable candidates would be functions that take less parameters than I have arguments, or more parameters than I have arguments. Functions that expect things that I cannot convert to, like here in this example, for instance, a standard string. Or, last but not least, functions that have constraints that I cannot match, so violated constraints. So I already have removed a couple of the candidates, and I'm left with viable candidates. With these viable candidates, I now try to find the best match. I determine from all of these functions the one function that I should call in the end. In order to make this a little simpler, I am now just passing a single argument. I'll tell you afterwards how we deal with several parameters, but for understanding the thing, a single parameter is probably good enough. So the first thing I do is I actually rank things. The best thing that can happen to me is an exact or identity match. The second best thing that could happen is that I just have to add a const or something trivial. These kinds of trivial conversion are also absolutely fine. These two things are ranked as 1. Officially, there is in the standard the specification that this is a rank 1 match. Then there is something called a promotion. And of course, a promotion could be combined with a trivial conversion. These two are ranked as 2. So they're not as good as rank 1, but the second best thing. After that, I have standard conversions. And of course, also standard conversions plus trivial conversions. This is ranked 3. And as such, it is not as good as an exact match or so a rank 1 or a rank 2. But it is still better than a user-defined conversion, with a trivial conversion, or a user-defined conversion and a standard conversion. These do not have an official rank, but mentally we can give it a rank, of course, like a rank 4. And the last thing that could happen is calling an ellipsis argument. This would be something like a rank 5, unofficially, of course. Now let's take a look at a couple of examples. So let's say that I have an integer, 42, and that I pass this to a function f. Lookup came up with these two functions. Function f that takes an integer reference and a function that takes a double. Now the process is pretty simple. I rank these functions based on the given arguments. For function 1, I actually get a rank 1. It's an identity match. I don't even have to add a const here. For function 2, I rank this as a conversion, so a rank 3. So it's obvious function 1 should be called because it has a much lower rank than the second function. So function 1 is called. If in this example I add a third function, a function takes a constant integer, it becomes a little more interesting. Function 1 is still ranked 1. Function 2 is still ranked rank 3. And the third function is actually also ranked 1. A trivial conversion is still a rank 1. Still, intuitively, we would argue that function 1 is a little bit better because after all, the int that I'm passing here is not const qualified. So we believe the identity match is better than a trivial conversion. Still, they're both rank 1. This is why we need a tiebreaker. If you, for instance, go to CPP reference, you will actually find a very, very good article about overload resolution. It is a pretty lengthy article, but it is definitely worth to read in its entirety to get a better feeling of what is possible. So I simply scroll down now to the point that gives us an indication what happens in this particular case. So we are ranking implicit conversions now. And it says a standard conversion sequence S1 is better than a standard conversion sequence S2 if, now we have to scroll down a little more, if both S1 and S2 are binding to reference parameter, only different in top level CB qualification, and S1's type is less CB qualified than S2's. So it also gives the example that I just have, function f that has a constant ref and an int ref. And if I just pass an int, which is not const qualified, the first function should win. So this is exactly what happens here too. This will call function 1 thanks to this special rule that breaks the tie between these two rank 1 functions. So if indeed two functions are matched equally, so for instance, in this example, where I have two functions, f, one takes a float, function 1, one takes a double, function 2, and I pass an integer, then both functions would be ranked as standard conversion, rank 3. Yes, it's different standard conversions, but still none of them is considered better. It is both rank 3. There is no special rule available. This function is now ambiguous. Same rank, no special rule. If you have an ambiguous function call, as I said before, there's no going back looking for other functions. This is a hard compilation error. It would stop at this point, and you would get an error message that pretty clearly expresses that the compiler cannot decide which function to call. Usually, we'll also get a list of all functions that are considered viable candidates, and you will see close matches for those that are considered as best matches so far. There is one very interesting special rule that is also to some extent confusing sometimes. Let's keep the example as it was before. I call a function f with an integer, but now the two functions are a non-template, function 1, and a template, where I use one of these new fancy C++20 concepts. Both functions are viable candidates. In the argument deduction phase, function 2 is transformed into a function you can actually call, which would be something like that. It's a function resulting from a template, and this function takes an integer 2. The interesting thing to note here is that these two functions are now virtually identical. That can happen due to template instantiation. I have two functions that take exactly the same argument. And still, we can come to a conclusion. So, of course, both would now be ranked 1. Again, there's a special rule in the overload resolution set of rules. So, it is this one, f1, function 1, is determined to be better function than f2 if implicit conversions for all arguments of f1 are not worse than the implicit conversions for all arguments f2, and, special case, f1 is a non-template function, while f2 is a template specialization. Specialization used here as instantiation of a template. So non-templates, if indeed they are equally well matched, have preference. So in this case, function 1 would be called. This usually only happens if you really have best match or identity matches, so rank 1s, because templates tend to be exact matches or identity matches. But in that case, the non-template is preferred because else it wouldn't be called anywhere, couldn't be called anywhere. It's a pretty reasonable rule. So let's talk about promotions, rank 2. The standard defines a small set of special conversions, which we call promotions. So for instance, an unsigned short can be converted to an unsigned int, or int, depending on your platform. A short can be converted into an int. A jar can be converted into an int or unsigned int, depending on your platform. And a bool can be converted to int. That is integral promotions. And there is also one available floating point promotion. Float can be converted to double, and this is considered better than other kinds of conversions. So rank 2 promotion is considered better than any other kind of conversion. So for instance here, I have a short, again set to 42, and I call f with this short. I only have a function f that takes an int and one that takes a double. From everything I've said so far, you would assume it's both conversions, but now I mentioned these promotions. The first function is actually a special kind of conversion, short to int. It gets a rank 2, and the other one gets only a rank 3. So function 1 wins because it is better ranked. So as a lower rank, I prefer the promotion to the standard conversion. If instead I would have a float, then also typos, it shouldn't be called f, but then in this case, I would actually prefer the second function. The first would be a standard conversion, rank 3. The second would be a promotion now. Float to double is a promotion. So this calls function 2 in this example. Everything else, everything that is not a promotion, is a standard conversion. And there is a whole bunch of possibilities here. There's, of course, integral conversions, conversions between two integers. There is floating point conversions, conversions between two floating point numbers. There's integral to floating point conversions and also floating point to integral conversions. There is pointer conversions. So, for instance, you can always convert a derived pointer to derived to a pointer to base. And you can always convert a pointer to void pointer. Bool, a lot of things can also be converted to bool. So integers can be converted to bool, just as any expression that evaluates to anything that can be converted to bool. So one example, if I have an unsigned int, 42 again, I put this into the function, then this function, this can actually be called. I would simply convert the unsigned int to double, and this would be ranked 3, standard conversion. If I would have a function that takes an int, it also could be called. This would be a conversion from unsigned int to int. So again, this is rank 3. I call function 1. Interestingly, and perhaps a little unintuitively, if the functions f with double and function f with int come together, then this call here is not calling function 2, despite the fact that this is integral. No, both functions are considered standard conversions. Both are ranked with 3. There is no special rule to say that this unsigned integer should go to the int. This will again be an ambiguous function call. Same rank, no special rule to keep them apart. So standard conversion, even if it is an integral to integral, is not better than any other kind of conversion, which is again something that is supposed to protect you from unfortunate conversions. Of course, this works, as I said before, in class hierarchies as well. So just as one quick example, let's consider a class A that is used to define a B, which is used to define a C. If I have two functions that, one function that takes an A pointer and one function takes a B pointer, function 1 and 2 again, and I have a C and pass the address of C to this F, then actually function 2 would be called. Both are pointer conversions, both would be ranked at 3, but for that particular case, there's again a special rule that actually helps to disambiguate. So this will call function 2 because the pointer to C is a little closer to the pointer to B than it is to the pointer of A. Pretty reasonable and intuitive again. So again, here it works in this way as you would expect. Everything that goes beyond standard conversions is user-defined conversions. So for instance, if a widget class that I define myself has a constructor that takes an int and a constructor that takes a double, these two constructors, which both are non-explicit, can be used to convert from fundamental types to widget. And also, you could have in a class so-called conversion operators. They're curious because they do not have a return type, but the return type implicitly is the thing that you are mentioning after. So this conversion operator allows you to convert a widget into an int. This conversion operator allows you to convert a widget into a double. Both constructors and conversion operators can be used for user-defined conversions. For instance, in the following way, again, I have an integer that I pass to a function, and now I have two functions f. One takes a long, one takes a widget. And note, again, the widget has a constructor that takes an int, so I can construct a widget by means of an int. In this particular example, function 1 would be ranked 3. It would be a conversion from int to long, so a standard conversion. The second function, however, is ranked as a user-defined conversion. So in this particular case, function 1 wins. Despite the fact that this widget takes an int and I have an int. Either way, standard conversions are always ranked better, considered to be better than any kind of user conversion, even if it appears to match better intuitively. So there is also one special rule that explains this pretty well in the ranking of implicit conversion sequence part. A standard conversion sequence is always better than a user-defined conversion sequence or an ellipsis conversion sequence. So indeed, we can think of a user-defined conversion as an unofficial rank 4, which doesn't exist officially, but we can imagine that it indeed is ranked as such. Now, if you have user-defined conversions only, like here in this example, we have a widget that takes an int, a constructor that takes an int, and a widget constructor that takes a double, constructor 1, constructor 2. And I have a function that takes a widget, and I call this function by means of an int. Again, the intuitive things happen. It is a user-defined conversion because I have to create a widget from this integer. But constructor 1 is just a user-defined conversion, whereas constructor 2 is a user-defined conversion and a standard conversion. So integer has to be additionally converted to a double. This is why constructor 1 is considered better match. So I call function 1 and function 2 is not considered anymore. If, however, I have a short, again set to 42 and call function f accordingly, then this is a user-defined conversion plus a promotion, whereas function 2 is again a user-defined conversion plus a standard conversion. A promotion is always better than a standard conversion, so I again consider function 1 the better match and call function 1 instead of function 2. There is the according the descriptions again in CPP reference, or of course the standard itself. We just have to scroll down a little bit and go to item 4 here. A user-defined conversion sequence U1 is better than a user-defined conversion sequence U2 if they call the same constructor / user-defined conversion function or initialize the same class with aggregate initialization. And in either case, the second standard conversion sequence in U1 is better than the second standard conversion sequence in U2. So if I do have a user-defined conversion in both cases, I pick the one that is better with regard to the following, the subsequent standard conversion. Now, this explains how the compiler selects a single function, a function with a single argument. But what about multiple arguments or multiple parameters? This process is actually just a consequent application of the rules that I've explained so far. For several arguments, the compiler applies the same rules to every single argument. If one function of the ones in consideration is considered better for at least one argument and equally good for all the other arguments, then this function is considered a best match, else the function call is ambiguous. So for instance, consider these two functions, function 1 and function 2. The first function takes 3 integers. The second one takes 1 integer and 2 doubles. Now, I admit that this is a little artificial and probably will not appear in real code in this form, but it definitely explains what is happening. I'm passing an integer, I'm passing a short, I'm passing an unsigned integer. The first argument, the integer, is actually a rank 1 for both functions. At this point, I cannot make a decision. The second argument is actually a promotion for in the second case, in the first function, that is a rank 2, but it would only be a standard conversion for the second function. And the unsigned int, that is a conversion in the first and in the second case. Because of the second argument, because this is a promotion only, function 1 is actually a little bit better than the second one. Function 1 is at least as good in all the arguments as this one, but 1 is better. And so function 1 is selected and called. It's considered the best match. If I change the second argument from an unsigned int to float, things change a little bit. Still, I can consider the first one as a tie between these two functions. I can consider this a promotion and this a conversion again. Now the float is converted into an int, rank 3, but promoted to double, rank 2. Now in both cases, and for both functions, I have one argument, one parameter, one case, where it's better than the other function. As soon as this situation arises, and it's completely irrelevant how many other extra points the other function gets, so how many are better, as soon as both functions have one argument that is better, this is considered an ambiguous function call. So the compiler does not make a decision here. You have to disambiguate by cleaning up the arguments. Which, however, shows that complex situations should be avoided. So one of my guidelines for you would be to prevent complex overloading situations that may result in surprises during overload resolution. And also consider core guideline C163, overload only for operations that are roughly equivalent. So it really pays off to only overload if things are really doing similar things. So the overload situation should be easier to resolve, should be more natural. All right, this was a big subchapter. If there's any questions, please post them. I will take them at the end, try to answer as many questions as possible. Which brings us to the access labels, which may seem a little boring, but surprisingly, there's a lot that we have to consider as well. And this is one of the examples that is also confusing for beginners in C++. I have a class called object, which comes with two functions f. The first function f is in the public part and takes an integer, my function 1 again. Then I have a second function f that takes a double. That one is declared in the private section of this object, my function 2. Now I create an object and I call function f with a double value. A lot of students now argue that, of course, this must call function 1. It's the only public function, and as such, it's the only thing that I can access from outside. Well, in this particular case, this will result in an access violation message from the compiler, which essentially means you're trying to call function 2, but unfortunately, this function is declared private and therefore cannot be called. Perhaps you already understand this based on what I've said before. The very first step is name lookup. We start in the scope of object because this is where we start to look for the function, and the compiler finds both functions. At this point, these labels are not taken into account at all. There is two functions f. There is no template, so I go to the overload resolution, which decides that function 2 is the better match. I have a double argument, and so it's an identity match here, but it would be a rank 3 call here. So function 2 is selected. Only afterwards, I actually take a look at these labels and find that this function has been put into the private section. I have an access violation. There is a very good reason why it is working in this order, because again, it is supposed to prevent you from surprises. Regardless of from wherever I call this function, wherever I have a call to f with this double value, it should always resolve to the same function. So regardless of whether I call this from the outside, like here, or somewhere inside the class, it still should resolve to this one function. No change, no difference here. And so this label here is indeed checked after the overload resolution, which means that this here is truly an access label. It is not a visibility label. In C++, everything inside a class is visible. Everything. And it's basically led to the introduction of a new keyword in C++20, which is glass. Yeah, we have indeed a glass object. Now, of course, this is a joke. Yeah, so there is no glass keyword, but actually it would very, very nicely express what this truly is. This is something where you can see everything, but you cannot access everything. And so Please consider these labels as truly access labels. Remember that everything inside a class is visible. Public, protected, and private are merely access labels. Yeah, this is very different from other programming language, and as such, indeed, a little surprising. Okay, if you have questions, please again write them down. The next step would be function template specialization, which is a step that I cannot really go into detail. But at least I want to give you a feeling that this is indeed a step that happens very, very late. The first function I have is a base template, a function f that takes some t. The second function is a function template specialization. I specialize this template for character pointers specifically. The third function is a base template again that takes t pointers, t being any type. If in the main function I have initialize a chart pointer and then call a function, surprisingly, it is not this function that is called, but function 3. Function template specializations are not considered during the overload resolution, but only here in this step. Only function 1 and function 3 are considered during the overload resolution. At this point, the compiler finds that function 3 is actually better matched. It is dealing with pointers, whereas function 1 is taking any type. So because function 3 is a little more specialized for pointers, function 3 is selected and ultimately called. Function 2 is a specialization of base template 1 only, and as such, only if this base template is selected, this specialization can be taken into account. The game changes a little bit if I switch function 3 and 2, because suddenly this here is a specialization of function 3. Before it was defined before, so it couldn't be, but now it specializes this function. Now with the same call in a code in the main function, I actually call function 2. Function 3 is selected in the overload resolution, and now in this step, I can consider its specializations, and function 2 is better. It is more special for chart pointers. Note that sometimes syntax gets in the way. You're also allowed to define this function f in this form. You can explicitly say how you're specializing it. This, however, unfortunately, is now again a specialization of function 1, because this t here matches this perfectly. It's not the same pattern as in function 3. Therefore, if I select function 3, there is no specialization anymore, and again, I would call function 3. This is just something to keep in mind, and also it is important to keep in mind that function template specializations are considered only after the base template has been selected. So the takeaway is prefer function overloading to function template specialization. But admit that this was rather short. I refer you to an excellent talk given by Walter Braun on C++ function templates. It's a 1 hour, 20-minute talk just on this topic. And after this talk, you will truly know everything that there is about function templates, including how they interact in overload resolution and this entire call mechanism. All right. Which brings us to virtual dispatch, which I said I will not explain in detail. Again, I can only forward you to an excellent talk by Stefan Tilave, which is not just one talk. There's actually an entire series of talks called Core C++. The fourth part is the one that you're interested in if you're interested in virtual functions. And this is where he really explains pretty well how virtual dispatch works in detail. Highly recommended. And also, of course, watch the other Core C++ talks about name lookup, function template, argument deduction, and of course, also overload resolution. So this leads us to the last step, deleting functions. Let's consider that I call a function f with 42, and I have two functions. One takes an int, one takes a double. This double function is explicitly deleted. Then, perhaps surprisingly, this function here, non-surprisingly, this function will call function 1. No problem. If I call function f with a double, however, it is not calling function 1, but instead you get a compilation error that you're trying to call function 2. Equal delete is not changing anything with regard to the declaration, and it definitely does not get rid of this function. It does not remove it. On the contrary, equal delete is a definition that says this function has no implementation. So function f that takes double, function 2 does exist. And if you try to call it, you will get the according compilation error. So equal delete doesn't delete a function, despite the name, but declares it as uncallable. Any attempt to call a function will result in a compilation error. This is something that, of course, you can use. If indeed you have a function that must not be called, you can explicitly delete it in order to make it perfectly clear to a caller. But of course, there's also implications. And you might remember the rule of 5, which is C21 in the core guidelines, that suggests that you delete some of these special member functions whenever necessary. However, deleting, for instance, the move constructor has different implications than not writing it. If I delete the function and try to call it, then I get a compilation error. I must not delete. You called the delete, you must not move. You called the move function. It's a compilation error. If I omit it, however, then the implicit fallback is copy. And suddenly this works by calling the copy constructor. So indeed, deleting something explicitly makes a difference. So please remember core guideline C21, and also remember that sometimes not writing some functions may actually express better what you have in mind. So, which brings me to the summary. This was now a complete overview of the individual steps in calling a function, the complete mechanics from name lookup to deleting functions. I hope this was helpful in order to get an overview of what happens, and I highly encourage you to take a closer look at either the CPP reference page that I showed or the standard in order to get a full and complete overview. So thank you for your attention, and perhaps there is still a little time left to answer one or two questions. Okay, and indeed there is one. What are pointer conversions considered? For instance, I suppose conversion from a short pointer to int pointer is not a promotional, like it would be for short and int. Absolutely correct. Pointers are special in this regard because you don't want to deal with, what do? You don't want to deal with short values as integers. That would require you to use a reinterpret cast. You explicitly would have to tell the compiler, please treat these underlying shorts as integers. This is not a valid conversion at all. So this would be a function, if you have a function that has a short or int pointer, and it would call a function with the other kind of pointer, it would always be considered a non-viable candidate. So indeed, pointers are different in this regard. Second question, can you quickly explain two-phase name lookup versus an early example where a matching function was declared after the calling template function? So there's unfortunately no slide numbers. So this is a little tricky to explain. I don't know exactly what you're referring to. So please find me afterwards at the conference or contact me any other way. Probably you can figure this out. And as a third question, slide 105. This is something I can go back to. Delete. If you call f with a 1.0 f, we get a compilation error because the compiler tries to promote float to double instead of performing a standard conversion. Absolutely correct. Yeah, you basically got the idea. The name lookup finds both f, overload resolution detects or determines that the second function is better. And at the very end of this entire pipeline, I actually figure out that this is a deleted function and that it must not be called. So if I pass a float, it still is a compilation error because function 2 is selected. Okay, and there is a question about slide 65, which I'm going to have to find real quick. 65. Don't reference conversions work pretty much the same as pointer conversions, minus conversion to void. It is not explicitly listed as far as I know, but I may be mistaken. Perhaps I just overlooked this. It actually works in a similar form. Absolutely correct. I didn't list it here because I didn't see it. I think if you have a derived reference and you pass to a base reference, of course, it works in exactly the way that pointers work. So perhaps I just failed to mention it. Either way, thanks for the reminder. Okay, and that's it. Thank you very much for your attention. Thanks for choosing this track. I hope it was a helpful talk for you. Thank you.